All right, hello again, Ling statisticians. We're getting kind of a late start on tonight's video, so hopefully you will still be able to see my face by the time this video is over. But even if you don't, I guess it's not that important. What's more important is that we're going to talk about something called confidence intervals today. And I kind of got ahead of myself a little bit at the end of the last lecture in two different ways, so I kind of wanted to walk into where this is coming from before I talk about the technical specifics. So for a moment, let's go back to our big goals for this class that we talked about at the beginning of the semester. Right now, what we're going to do is transition or start transitioning from data reduction, where we talk about, simplifying our picture of data, like by talking about means and standard deviations and the shapes of distributions, so on and so forth, to something called inference or hypothesis testing. So looking at data and trying to figure out what story it tells us about the bigger world. We've kind of talked about that a little bit already in kind of delineating the distinction between populations and samples, that sort of thing. We're going to dig into that further, though, starting with the lecture today. Inference is something that is not, just part of statistics by itself. It's something we do a lot of in linguistics or science in general, I guess you would say. But we do it in different ways in linguistics than what we will wind up doing in stats. So this, kind of leads into the other way I was getting ahead of myself last time. But I want to draw a parallel with a distinction I talked about last time, and I just mentioned this one. So there's populations and parameters, and they contrast with samples and statistics. And you can kind of look at that sort of like an analogy with phonology and phonetics if you're on the sound side of language. So phonology deals with sort of these abstract idealizations of sound, and phonetics deals with what's on the surface when people actually say things or what sounds they actually produce. And you can kind of look at that like, well, when I'm looking at phonetics, I'm taking a sample of sort of the sounds that come out of somebody's mouth, but it's not necessarily the abstract ideal or the complete picture of what that sound represents. And I kind of have to make a leap from the phonetics to figure out what's going on in the phonology, sort of, as we say, underlyingly in the phonetics, but you could also think of it in terms of like sort of a higher level existence for the sounds in the world of phonology, like some sort of ethereal plane maybe, or platonic reality. I don't know. Either way, it's not something you can observe directly, which is kind of the important part to keep in mind here. And to see what I mean, I wanted to show you a very basic phonology problem, and I inadvertently talked about this problem at the end of the last lecture because I put these notes together before I recorded that lecture. And so if you watch that video and are like, what the heck is he talking about? Sorry, but this is what I was talking about, this slide on the language Mocalese. So this is a demo or example problem I give to my intro classes based on the phonology of Mocalese, which is an Austronesian language spoken in Micronesia, the country of Micronesia in the Pacific. So you probably aren't familiar with Mocalese outside of, say, phonology class, but Mocalese has voiceless vowels. And I can give you some data from Mocalese. And what we want to look at here is where we're finding these voiceless vowels, what determines whether a vowel will surface phonetically as voiceless in Mocalese. And like I said, I use this as an example problem when I'm talking about phonology in my intro linguistics classes. And at that level, it can take a little while to figure out, but normally when I present this to sort of grad students and higher level students and undergrads in this class, people figured it out pretty quickly. We'll see how you do. So we have like a voiceless vowel in the form number 1 here. We don't have any number 7 or 8. Actually, what's going to wind up happening is that I'll give voiceless vowels on the left-hand column here and no voiceless vowels on the right-hand column. And maybe you can tell me what's going on after sort of thinking about this for a little while. I don't know if I have more examples here, but I'll stop at an even dozen. And hopefully you can see this, that what is going on is that oo and e in particular are becoming voiceless over here on the left. And they only become voiceless when they're in between two voiceless consonants, like K and S for the voiceless E and number 4, or say P and K for the voiceless oo, or T and P for the voiceless oo and number 2. But anywhere they're close to a voiced segment or on the edge of a word, it doesn't happen. And it also doesn't happen to, say, other vowels like ah in the language. Okay, so we're linguists. This problem, and we're experienced linguists too, so at this point, this problem is probably not super difficult for us to kind of see the pattern and figure out the answer. And we've learned how to do these sorts of problems over time, and maybe you had an aptitude for them to begin with. But what's kind of still maybe an underlying mystery here, haha, is like what exactly is are our minds doing when we're figuring out these patterns? So I want to keep this big picture distinction in mind. So there's observation and inference. I mentioned that briefly just a second ago. So we can observe on the surface, on the phonetic surface of language, like what sounds are being produced by which gestures or what sort of acoustic features do they have. We can see that directly. But what we can't see directly are these overall patterns exhibited by the sounds. Like, oh, we're only getting these vowels changing to voiceless vowels in this particular context. There's a pattern there, which we need sort of multiple observations to figure out. You can also think of this as sort of a distinction between description and analysis. As linguists, we're probably pretty good at analyzing things. One of the skills we have to develop as well as linguists is to describe things accurately as well. But how do you make those inferences? How do you go from just raw descriptions where you're just seeing things on the surface directly to jumping to these conclusions about what's happening in a patterned way in a language? What's the process? And maybe you can spend some time thinking about that as you're watching this video. I'm not going to spell out what these rules are because I just kind of want to ask this rhetorically. But I want you to think about what are the rules you have for figuring out patterns. How do you know if something's a pattern versus not a pattern in language? When do you have enough evidence to sort of draw some conclusions from your data and say, oh, that's what's going on here, as opposed to something else, or maybe nothing else for that matter? I have this question about what are the rules for jumping to conclusions, and maybe we can have some guidelines for what is a reasonable hypothesis to sort of put out there in linguistics, but there's not necessarily rules per se. There's rules for sort of knowing when you're wrong about a hypothesis. When you get an observation which contradicts what your hypothesis was, then you have not only have a falsifiable hypothesis, but it's been falsified in that case. And then some people just keep on going with the hypothesis and ignore it. But that's not really the way science works, or it ought to work at least. But there's rules for that, but there's not necessarily a rule for drawing those generalizations. You kind of like see the pattern, and maybe there's some sort of hidden algorithm in your head which just says, okay, this is the pattern that's going on, but we don't make that explicit. We just kind of see the pattern and go with it. And another thing that happens in phonology or linguistics when we're dealing with discrete data, like what we saw in the Mocalese, where I gave you just symbols, which had sort of clear distinctions between one form of the sound and another, our conclusions are bolstered by the fact that the patterns we observe appear to be absolute. Like, there are no exceptions to the rule here in Mocalese. Like, every single time we get an E or an U in between voiceless segments, it becomes voiceless. At least that's how we interpret it, right? And there's no contradictions to that on either side of the equation here. In reality, though, like if we're looking at this phonetically, we might make measurements of these voiceless vowels and say maybe there's partially voiceless, or in some cases they're partially voiceless, in other cases they're completely voiceless, so on and so forth. We might get a little bit of sort of quantitative variability there. In this phonological approach, we're just getting, oh, nope, it's all or nothing, whatever rule might be on either side, which is nice. It kind of fits with the way most linguists' minds work, I think, where we kind of see things in sort of nice absolute mechanical terms in language, and it kind of fits into this pattern and clicks and feels good inside. But the problem is life in reality, when we actually observe what's going on, is not that perfect, or really ever perfect at any time. And we have to deal with those sorts of imperfections. And lucky us, this is where stats comes into play, because it's a tool we can use in these sort of more ambiguous situations to try to draw inferences from imperfect data about what might be going on sort of underlyingly in sort of different groups or different populations. So in stats, we're going to be dealing with a lot of processes that have variable output, or maybe only apply in a not absolute manner. And one other moral I want you to keep in mind, and this is true if you're a phonetician or any sort of like experimental scientist, I guess, but there's variability in everything. And yeah, even like mentioning that, we're going to come up with like a system or an approach we can use to sort of look at our data and generate inferences from that data based on a set of sort of statistical criteria for what counts as like legitimate evidence that something is going on. And, you know, in a case like producing voiceless vowels or a certain kind of vowel quality or what have you, we can think in terms of, you know, variability are not absolutes because maybe something might be more voiceless than another, whatever. It's kind of easy to think about that in terms of language if we're used to getting, you know, empirical data from our studies. But this applies even in, say, like particle physics. The criteria in particle physics winds up being a lot more sort of stringent than what we do in social science. In theory, you know, it's easy to imagine like things working in an absolute like clock-like manner for like physical phenomena, like at the proton or like atomic level, what have you. But even when physicists go about their business and like collect data from a study, they evaluate it using these same statistical methods. They're just using sort of, again, a more stringent criterion for saying, well, this is actually something that's going on as opposed to something that's not. And the fact that we're not using criteria that are that strict in linguistics or social sciences in general can lead to some problems, but I don't have time to get into those right now. I might talk about those in a future lecture. Actually, I probably will. But just keep in mind, even at what you might think of as an absolute level of like how the world works, there's still going to be variability, and we have to evaluate it in terms of whether or not we want to jump to conclusions on the basis of what variability we're actually observing. So under these circumstances, we're going to establish a formal process for jumping to conclusions about the abstract parameters underlying the variability we see on the surface. And then we're also going to set criteria for how much evidence we need to see in the variability before we draw those conclusions. And like I said, these criteria will be stricter for like physics than they are for phonetics, but you know, we love both physics and phonetics, so let's just roll and see how this works. Okay, give me a second. One of the ideas underlying this process is something we've covered already to a certain extent. But first of all, we can play around with things, you know, like normal distributions, something we've seen before. And using those normal distributions, we can use the mathematically defined connections between z-scores, which we've seen before, and the proportions of the distribution to draw these inferences. So we're going to build on things that we already know. That's primarily why I talked about them to begin with. Also, we have to depend on the properties of the process of sampling in order to be able to do this reliably well. So there's a reason I talked about sampling as well. And this is some of the things that we talked about at the very end of the last lecture. So when we sample, we wind up with three distinct elements in our conceptual system. Number one, we have populations and the parameters that go along with them. So like every single, you know, item in a group, and then like their associated parameters like their means and standard deviations. And then like the other part of that is just the sample we take from the population, a small subset of that population. And that has statistics too, like means and standard deviations. And we're trying to draw an inference from the sample of data that we get about the entire population that we're actually interested in. And then in the process, if we do a lot of sampling of the same population, or just in general, there's a mathematical sort of construct we can develop called a sampling distribution, which has as its individuals or items in the distribution these statistics from the samples we've taken of populations. And this number three, this third element in our system, is a very sort of meta kind of idea, but it's going to be useful because it helps us relate what we know from number two to what we want to know about number one. So 3 is a magic number. Population distributions are what we get when we tabulate the characteristics of every individual in the group. And these distributions have parameters like means and standard deviations, so on and so forth. I'm just walking through exactly what I said before on the previous slide. Actually, I don't know why I put this slide up here again. Samples are formed from subsets of the population, and then in a sampling distribution, the individuals are the statistics of samples. And the relationship between 1 and 2 is important, because we're just able to look at this. This is the phonetics, the surface, the observational side. And then number 1 is what we actually care about. It's sort of the underlying or, inferred sort of element in this equation. But it's what we really want to know about. It's sort of like the phonology side of what's going on. And in order to make that connection, we make inferences about the population from the sample statistics. Okay, this is where I left off last time. And I think since this is a little bit of review, once I talk to you again about the central limit theorem, I'm going to pause this video so it doesn't go on too long. Like I said, it's getting laid out outside. But the central limit theorem is going to be the key to sort of tying these various elements together. So the central limit theorem describes the properties of the relationship between the distribution of sampling statistics and the populations from which they are drawn. Okay, so we've seen this before. This is review, but it's useful review, hopefully, because this is the connection that gets made. So property number one described by the central limit theorem is that as the number of individuals selected in a series of samples increases, as n gets bigger, the distribution of the means of those samples will approach normality. So n here, number of individuals in a sample, that's a property of the sample itself, or any given sample. But then when I start to sort of plot out the statistics of those samples into a distribution, a sampling distribution, we start to see this property emerge. So the distribution of the means of those samples will approach normality. And I gave you an example of that last time where we looked at like the distribution of F0 from just class productions of individual words. And we found that that distribution itself is not normal, it's skewed right. But if we start to take means of samples from that distribution and plot those means, we get a normally distributed sampling distribution. But this applies sort of across the board as long as you get sort of a sufficiently large number of individuals in each sample as n gets bigger. It's a little bit like calculus, is that we're sort of approaching like a tendency is n gets larger. This will happen even if the population distribution itself is not normal, so you don't get normality just from underlying normality, you get it from wherever. And again, all that has to happen there is for n to be sufficiently large. Number two, the second property of the central limit theorem is that the mean of the sampling distribution will be equal to the population mean. Yeah, and this kind of speaks for itself, I think. But what matters here is that we want to know what the population mean is in various circumstances. Like I said, we're trying to draw inferences about that sort of underlying level of structure in the data. And we can't observe it directly because it's just too hard. It takes too many resources to do that. But we can get a read on what the mean of the sampling distribution might be. So, yeah. The other thing to keep in mind here is normally we're just taking one sample from a population. And in that case, the circumstances or sort of the situation will normally say, in those circumstances, we're normally going to get a sample mean that is not exactly equal to the population mean. It might be fairly close to the population mean. It might not actually be all that close at all in some cases as well. Keep that in mind too. But we want to be able to use that sample mean to figure out what the population mean is. And so we're going to try to do that in part based on these first two properties, knowing that our sampling distribution mean should be equal to the population mean. And then we're going to use property one as well, knowing that the sampling distribution will be normally distributed as well, to try to give us a sense of how that individual sample mean relates to the population mean. And I'm sorry I'm talking in sort of gross abstractions here throughout this, but I just want to set the table, as it were, before I start giving you a few examples. And then the last property, which we've talked about before as well, is the standard deviation of the sampling distribution. Will not be exactly the same as the population standard deviation. Instead, it's going to be that underlying population standard deviation divided by the square root of n, the number of items in the sample. And when you do this, you get a standard deviation, which is known as the standard error. So standard error is the standard deviation of the sampling distribution itself. And in theory, it's equal to this as long as n is sufficiently large. So we're going to use these properties to make this connection between the individual sample data we get and the populations that they are drawn from, our understanding of those populations. But like I said, this is just sort of walking you through the basics or the theoretical basics. I want to talk about a few specific examples in the next part of this video, but for now, I'll just keep this as it is and watch the darkness rush in. Okay, I'll see you again in just a minute.